There we go. There we go. Now we're going. Now we're cooking with gas. Here we go. All right. How's it going? How's it going, everybody? Eighth grade, if you're live with me or on demand, I'm going to get started here and just kind of get right into it. Um, Hope everyone's doing well. Hope everyone's doing well. This is May 12th, 2020. Almost halfway through the month of May already. Crazy to think that we talked yesterday in the May 11th stream was talking about scientific notation with audio. There we go. We were talking about scientific notation and dealing with the fact of saying, instead of writing out a number such as this, it almost looks like I can't even write that many numbers. There we go. If I wrote this number, 32, I believe this is 32.5 trillion. Yeah, because this is tens, this is thousands, this is millions, billions, and then this is trillions. I believe I'm sure someone can correct me if I'm wrong on this, but this is 32.5 trillion. I don't think you all want to write that down all the time. So a lot of times what ends up happening is that we utilize what we call scientific notation in this instance. Scientific notation, just to remind, is a simpler way. It's a simpler way of taking this number that we see right here, which, if you remember from yesterday, was written in standard form. This was written in standard form. There we go. Remember, that was written in standard form. We want to write it now in scientific notation. It requires, in this instance here, one second, I'm sorry. There we go. Better. Hey, Raquel, how you doing? How you doing? Hi. Hi. Everything's going good. So talk about this number that was in standard form. So just remember on this, you know, it's it's taking two factors. It's taking two factors that you see right here and making it easier to write. So instead of writing 32.5, 32 and a half trillion every single time, we can sit here and say, how many times am I moving over to the left? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's 13 times we're moving over. And remember, this first factor needs to be between 1 and 10. It has to be between 1 and 10. Above 1, it has to be above 1 and below 10 when writing something in scientific notation. So we move our decimal like we did all the way over to where we get to that first number, as you see. Hey, what's up, Brianna? How are you doing? So when we move that over right there, we find out that that first factor can now be 3.25. 3.25. And then times 10. And how many times did we move that decimal over? Remember, we moved it over 13. What's up, Kennedy? How you doing? We moved that decimal 13 times to the left. So taking this number here, yellow, this number was written in standard form, while this number was written in scientific notation. That was written in scientific notation. Okay? It's just manipulating the decimal and utilizing a second factor so that you don't have to write out 13 zeros all the time. Just remember, I mean, you have to first like identify that initial leading number right here. You can do this. This part right here is quite simple. Okay, right there. Let me do another quick one real quick. So if I had the number 20 million, 20 million, 20 million is written in, that is written in standard form. So standard form. Let's write it in scientific notation. Science. First identify. Always remember, it is always a 10, by the way. Here. Scientific notation is always going to be a 10 in a math sense here. So I put the box to show what, how many times we're moving that decimal over. So now in this instance, how many times am I coming across? 3, 4, 5, 6, 7 to get that first decimal or first number that is going to be above 1 and below 10. So it's going to be 2. And we move that how many times? 1, 2, 3, 4, 5, 6, 7 times. 2 times 10 to the 7th would be our scientific notation. That's just reviewing this. I hope that makes somewhat sense. Okay? Maybe if you're following with me live or you're on demand with this, if it's something to kind of just, refresh your minds with, I hope that helps a lot. You'll see scientific notation. You'll see scientific notation. When you're dealing with, equations with like rational exponents and all this good stuff, and it's like, oh God, what is this? I laugh like I laugh just because I remember doing this myself, and it's like you go through some of this stuff, and it's like, oh my goodness. But what we're going to talk about here, in a little bit of time we have, is now talking about finding differences in these. So if I had, like in the instance, I want to compare the size of the Earth compared with the size of the Moon. So if we compare the size of the two numbers, we compare the two masses here. So we have the Moon's mass, which is about 7.35 times 10 to the 22nd kilograms, and the Earth, which is, as you can see here, which is 5.97 times 10 to the 24th. Now, there's two ways you can find, if we were to subtract the Earth, if we were to subtract the Earth, or the Moon's mass from the Earth, we can sit there and we could, obviously write out 5, 9, 7, and write out all these zeros. But we can use scientific notation to be able to do this. Here's the key. If I have two numbers here, we have the Earth. We have the Earth at 5.97 times 10 to the 24th. Okay. I'm going to put the Moon's mass down here for a reason. 10 to the 22nd. Okay. When we subtract two parts of scientific notation, we need to have the same exponent on this. And this is where it gets a little bit kind of not tricky, but yet in this specific instance of seeing this on a computer, it kind of might seem a lot confusing at first. But I want both of my exponents to be 22. How can I do this? I can factor out a 10 to the second here. Why can I do that? You remember from your exponent rules way back, 10 to the second times 10 to the 22nd is actually going to be 10 to the 24th. Okay? It's taking like 2 or 3 steps at one time to be able to sit there and say, well, now I can take 5.97 times 10 to the second, or 597 times 10 to the 22nd. And let me kind of move this over. I wrote a little too big. My fault. It's 597 times 10 to the 22nd minus, now we can put that moon's mass of 7.35 times 10 to the 22nd. Here comes the next part. We can be able to then take our two numbers here and put them together. 597 minus 7.35 times 10 to the 22nd. With scientific notation, we can do that when it comes to subtracting here, subtracting two numbers. So, what is 597 minus 7.35? It is 589.65. So it's 589.65 times 10 and to the 22nd. Are we done? Not yet. Remember, scientific notation needs to be above 1 and below 10 when looking at this first amount. What do we have to do? We have to move this decimal 2 to the left. When we move that decimal 2 to the left, it's going to give us, oh, that's a really bright, it's going to give us 5.8965. Thanks, Kennedy. If it's boring, then leave. 5.8965 times 10 times 10. There we go. 5.8965 times 10, and you're going to add those two to the exponent right there. 10 to the 24th. I appreciate you staying on here with me, Kennedy. That's good. You get to see the whole the whole kit and caboodle of everything, which you'll see coming in. All this fun stuff about finding masses and scientific notation, but it's fun stuff. It really is. So, this right here is your scientific notation. 5.8965 times 10 to the 24th kilograms. That would be the difference in the Earth's mass from the moon's mass. Okay. If we were together in class, we would go over this multiple times. But for the sake of time, I'm going to move kind of forward here with this. And this is just kind of, this is just going over this to kind of, refresh and all that kind of good stuff. It's this go off of here. So if we look at our differences here, we look at our little example here. It says the Confederation Bridge connects New Brunswick to Prince Edward Island. The main part of the bridge rests on piers that form 43 segments. So what is the approximate length of the main part of the bridge? The main part of that bridge in this instance, that main part of the bridge, obviously, is the bridge that you're driving on. So we are now going to multiply. We're going to multiply this distance between the pier 43 times. Now, could we take 43 times 8.2 and then multiply by 10 to the second? We could, but for the instance of dealing with scientific notation, we want to change this into scientific notation, and if you can kind of do it in your head, that's 4.3 times 10 to the first. So 4.3 times 10 to the first, and then you have 8.2. I try. I know. I know. This is. I think if we were like in class with this, I think we would try to make almost paper mache things, kind of make a bring the Legos and make a block and see how many centimeters it'd be across and all this kind of stuff to try to do what we can. Like I say a lot of times, math is not always the most fun thing. I say funnest. Oh my goodness. But in this instance right here, we change both of our things here. We have 8.2 times 10 to the second times or 4.3 times 10 to the first. What do you think we can do? I'll boggle the mind even more here. We can change the numbers around. So 8.2 times 4.3 times 10 to the second times 10 to the first. 8.2, 8.2 times 4.3 is going to give us 35. 26. It's going to give us 35, 26 times, and then that second factor, 10 to the second times 10 to the first is 10 to the third. And to put it into scientific notation, we're moving that decimal one to the left. 3.526 times, it's going to be 10 to the fourth feet. Okay? Almost there. Almost there. So we talked subtracting, which adding works the same way in that instance. Let me actually go to the try part here. All right. Next. There we go. So there are 1 times 10 to the 14th good bacteria in the human body. Why they make this explanation for this question, I guess maybe just to make people laugh. I have no clue. But it says there are 1 times 10 to the 14th good bacteria in the human body. There are 2.6 times 10 to the 18th good bacteria among the spectators in a soccer stadium. Don't know how that happens, but about how many spectators are in the stadium? If there are this much among spectators, and spectators, you're in a stadium, and that's the bacteria is through the whole part of the stadium, right? If you're setting up what we're going to be setting up, which is a division problem, I'm going to be putting 2.6 times 10 to the 18th up top. Okay, 10 to the 18th up top. What is in one person? It's 1 times 10 to the 14th. Now, let's go back. Let's go back to how we can do this. We can separate this into 2.6 over 1 times 10 to the 18th divided by 10 to the 14th. 2.6 divided by 1 is 2.6. If we have a division, if we have a fraction for division, in this instance, of 10 to the 18th divided by 10 to the 14th, if you remember from those exponent rules, we subtract those exponents. So 18 minus 14 is simply 4. So about how many spectators are in the stadium? A weird way to say it, but about 2.6 times 10 to the 4th spectators. How they get bacteria and spectators to do that, I have no clue. Okay, it's just running through running through that example there real quick, just to kind of give an idea of how to deal with scientific notation, and just kind of utilizing exponent rules and all that kind of all that good, wonderful gook right there, right? Soft here. Kennedy, if you're still with me, how's that working? Not fun stuff, huh? Let's see. All right. writing. Couple of questions on this, and then I'll be out of the way here. So for number one, I'll talk about number one. If you remember from what I was just talking about here, I can adjust our whole numbers to be in the beginning. If I see 2.8 times, you can read this. If I take the two here and I move them together, and I multiply by 10 to the fourth times 10 to the fifth. Okay. That's our first, like I said, that's our first step in that instance. Okay. If I take 2.8 times 4, it's going to give me 11.2. It's going to give me 11.2 times, and remember when we multiply 2 with an exponent there, we multiply 2 with an exponent, we add the exponents. So we get 11.2 times 10 to the ninth times 10 to the ninth. But we're not done yet. To put this in scientific notation, we have to make this above 1 and below 10, right? So above 1 and below 10, and I just got rid of the whole thing. But 11.2 times 10 to the ninth. We move our decimal 1 to the left, which makes it 1.12 times 10 to the 10th. And that right there would be your scientific notation for number one. Okay? That's your scientific notation for number one. Okay, just kind of moving quickly here. I'll kind of get this other one. If we're dividing 2, simply put, you can put 6 times 10 to the ninth over 2.4 times 10 to the third. You can separate it as this. And then 10 to the ninth over 10 to the third. 6 divided by 2.4 will give us 2.5. Will give us 2.5. And when we subtract our exponents, it leaves us with 10 to the sixth. 10 to the sixth. 2.5 times 10 to the sixth is that answer for number 2. Okay. And just for time's sake, let me go to number 4. The population of town A is 1.26 times, and you can go ahead and you can read that. Population of town B, 2.8 times 10 to the 4th people. How many times greater? How many times greater is the population of town A than the population of town B? This is another division here. It's another division with scientific notation. How many times greater is 1.26 times 10 to the 5th compared with 2.8 times 10 to the 4th in that instance? If I take 1.26 divided by 2.8, it's going to give us 0.45. So it's going to give us 0.45, 0.45 times 10 to the first. But remember, in this instance, if I or rewind it, 0.45 times 10 to the first is simply put as 4.5. Just how many times greater. It doesn't say anything about scientific notation, like leaving. It doesn't say anything about leaving it in scientific notation. It just says how many times greater. Well, you can do the math in this instance. 0.45 times 10 to the first is 4.5 times greater. 4.5 would be your answer for number 4. Guys, that's all I have. If you have any questions with me or for me, or if you have any questions, please reach out. Send me an email. Send me an email. Reach out over Google Classroom. I hope you all are staying safe. Please Please stay safe, stay healthy. I'll talk to you guys soon. Have a good week, guys.